Assignment 1T, Topic 1.7b. Our learning objective in this assignment is the same as the previous assignment with one modification. In this assignment, we are trying to figure out the end behavior of rational functions like this one right here, and we're doing it without plugging it into the calculator that graphs it, and without doing the table method that we showed you in the previous assignment. In this assignment, we should be able to look at the rational function itself and then determine the limit notation of the end behavior without having to use the calculator. Before we move on into the AP Pre-Cal part, let's make sure we remember 5th grade math. So if I have the number 2 and I'm dividing it by different numbers, let's see what happens. If I take two things and divide it up amongst 100,000 people, everyone's going to get a little bit. It's like if everybody won the lottery one week, not everyone's going to get that much money from it because everybody won, and we're dividing up the pot amongst hundreds of thousands of people. So when you divide by a big number, you get a really small number. If you divide a number by itself, it equals 1. That one should be pretty clear. The one that's less clear to some students is what happens when you divide by a decimal. And when you divide by a small decimal, you actually get a really large result, like 4 million here. So when you divide by a very, very small number, you get a really, really large number. All right, let's do example 1. I'm going to ask you not to write yet. I'm just going to show something mathematically to help you understand where things come from. So let's say I have this rational function where I have a linear function in the numerator and a quadratic function in the denominator. Remember our learning objective. Our learning objective is to figure out what happens to this rational function when x's get really, really big in both the positive and negative directions, as x approaches that infinity. So I'm going to demonstrate that by showing you what happens to this rational function when I plug in a really large number, let's say like 1,000,000, okay? Now in the numerator, I'm going to have 2 times 1,000,000 plus 3, and the denominator, I'm going to have 1,000,000 squared minus a bunch of other things. Well, we calculate that out. On top, I have 2 million plus 3. Now, if I was a person who had $2 million and then someone gave me $3 as a gift, that wasn't much of a gift. That $3 is insignificant to that 2 million. And the same thing, when we squared 1,000,000, we got 1,000,000,000,000. Wow, squaring big numbers really makes those big numbers even bigger. In fact, 4 million in comparison to 1 trillion and 32 specifically, these are insignificant numbers compared to that. So when I get rid of the insignificant numbers, I'm basically just doing 2 million divided by 1 trillion. And I'm going to get a decimal such as 0.000002. So I'm dividing by a really large number, which means I get a really small number as my answer. So now it's time to take notes. So when we're analyzing the end behavior of polynomials or rational functions, what we're going to do is we're going to cross through what are considered to be the insignificant terms. In other words, we're getting rid of everything except the leading terms. On top, 3 is not the leading term. I'm getting rid of it. And on bottom, the negative 4x and the negative 32, they're not the leading terms. I'm getting rid of them. That's because these 3 terms are insignificant to the things we're adding them to. So that gives me 2x over x squared using my exponential rules. 1x cancels out with the 1 on bottom, and I have basically 2 over x. And this is basically the function when you're looking at the edges of the graph. Now, if I plug in infinity into the denominator, meaning if I plug in really large numbers in the denominator, our result is going to be very small, practically 0. So my end behavior is 0. That's because the denominator dominated the numerator. This x squared beats the x. You will hear me often use that language of winning. The denominator won because it had more power. Let's confirm the answer by plugging in this rational function into the graphing calculator. And I can see as my numbers get larger and larger, my function is getting smaller and smaller, approaching that 0 value. And that's happening over here on the left side as my x's become increasingly larger in value, but more and more negative. My line approaches the 0. In other words, on the edges of my graph, I have a horizontal asymptote of y equals 0, that green line. Let's do example number 2. I have a rational function again. Analyzing the end behavior, we're going to ignore the insignificant terms. We're only looking at the leading terms. So 3x, 5x, and 12, those are not the leading terms on those polynomials in the numerator and denominator. I have x cubed over 5x squared using the exponential rules. I'm left with 1x in the numerator. That's just going to act like the graph x over 5. My end behaviors, therefore, when I approach infinity, this x becomes closer and closer to positive infinity. Dividing by 5, well, infinity divided by 5 is still infinity. So my limit as x approaches infinity of this function g of x is infinity. And because this is like an odd function, it's going to behave the opposite in the other direction. As I approach negative infinity, dividing that by 5 still gives me negative infinity. The limit as x goes to the left of the graph towards negative infinity gives me negative infinity as well. Let's plug that into Desmos and see if we got that answer. I plug in that rational function, and I can see as I zoom out that my function is ever and ever increasing in the right and ever decreasing in the left, verifying the answer I got. Also, I wanted to show you that when I do 1/5 over x, it creates this dotted line here, and you can see that the functions are behaving practically the same as we get closer and closer to the edge. Let's move on to example 3. So, same strategy. Have a rational function, looking at the end behavior. I'm going to get rid of all of the insignificant terms. In that case, 3 was insignificant. And now I have 2t divided by t. Now remember that anything divided by itself is just 1. So this basically says 2 times 1, which is approximately 2. So the end behavior of this graph doesn't approach 0 or infinity. Rather, it approaches the number 2. And it doesn't matter if it's negative infinity or infinity, because anything divided by itself equals 1. And that's what's going to happen. Let's look at it in the graphing calculator. I plug it into the graphing calculator, and I see the function is decreasing on the right. And it's decreasing, but it's not decreasing to the x-axis. It's decreasing to this 2 value. As I zoom out, and if I even write y equals 2, you can see that my function is approaching that horizontal asymptote. And speaking of horizontal asymptotes, let's summarize that real quick. So basically, there are 3 scenarios that we're looking at. What happens when the degree of the denominator is bigger? Well, when the denominator wins, the limits approach 0, so my horizontal asymptote is 0. If the degree on top or in the numerator is bigger, that means my number is approaching infinity, so there's not going to be any asymptotes. And if the degrees are the same, that's like they're dividing the same number divided by itself. You're basically going to look at the leading coefficients and their ratio. So let's do some examples. So the degree on bottom is bigger. With all of these terms becoming insignificant compared to the leading term, I now have 4x squared over x cubed, and the bottom wins. Therefore, my asymptote is y equals 0. When the degree on top is bigger, when I take away my insignificant terms, I have x squared over x, which leaves me an x in the numerator. That's going to approach infinity and negative infinity. There is no horizontal asymptote. And when the degrees are the same, getting rid of all of the insignificant terms and looking at the leading terms, I can see that my function on the edges is basically going to turn into the leading coefficient divided by the leading coefficient. The leading coefficient on top is 1, and the leading coefficient on bottom is 3. So that's going to approach y equals 1/3. All right, sometimes you will get questions like this where you're asked to evaluate the limit of an expression. Basically, it's the same thing. The question is, what happens as x approaches infinity of this expression? Well, on top, I can use the FOIL method to get that out, but I don't have to really think too much about it. I know that my leading term is going to be 2x squared, and everything else is going to be insignificant. And on bottom, the -9 is insignificant. So here, the degree on top is the same as the degree on bottom. Anything divided by itself equals 1. So that's going to equal 2. Let's do example 5. -9 is insignificant. On top, the 2 is also insignificant. But here, the numerator wins. That number is going to get increasingly larger on top. And I'm going to write out the leading term divided by the leading term. I get 3x. And if I plug in negative infinity into that x, I'm going to get -3 infinities. In other words, just negative infinity. So the answer to that one is negative infinity. Thank you for joining us today.